All right, now the whole of I mean, this is week number 3, right? So the last 2 weeks we talked about definition 1 of extreme values, right? So this week I gave you three definitions of extreme values, right? So this week I'm going to focus on definition 2 and definition 3. So I'll start with this one. I'm sure all of you know this, right? All right, this is definition 2. Definition 2 of extreme value, right? And before I start, do I need So definition of two. This is definition 2 of extreme value. So in this case, the extremes value are anything that exceed a threshold. So when I say threshold, I mean this line here. This line is known as a threshold. So which is a high enough line. If your data point is above that threshold, then it's considered an extreme value. Okay. Okay, so now I want to introduce some notation. Let me call this x. So x is the variable of interest. Can you see it or not? Can you see what I'm writing? So x is the variable of interest. So for example, it could be temperature in Manchester, right? Okay, and let me denote this point here by u. Let me denote this point by u. So u is a threshold. So for example, u could be, say, 30 centigrade in Manchester, which is rare. I mean, if you lived here for long enough, you would know that 30 degrees is not common in Manchester. So anything that goes above 30 degrees is an extreme value, right? So okay, let x denote the variable of interest. U denote the threshold. Okay. Right, and so the way we define an extreme value is if the value for x is the variable, is greater than u, then it's regarded as an extreme value. Okay. Now the question is, remember in definition 1, we talked about it last week. I mean, the last 2 weeks we talked about definition 1. And I showed you that the distribution of the extreme value under definition 1 is given by the extremal types theorem, which says that as n approaches infinity, it can be one of the 3 distributions, that is Gumpel, Fresche, or Weibull. So we need to ask the same question here under definition 2. What is the distribution of x when x is greater than u, right? So the answer to this question is given by the following result. It says that I need do you have the notes I gave you last week, or the original notes I gave you last week? Okay, I need to look it up. I forgot myself. Sometimes I forget things. Okay, thank you. All right, it says the following, that to answer this question, there is a result. Okay. Right. So the result says the following, that x minus u is the, you should look at this picture here, guys. X minus u is the difference between say, suppose this point and this point. So x minus u is simply the difference, right? Can you see what I'm saying? It's the exceedance. X minus u is this distance here, right? So x minus u is known as the excess amount. It's the excess amount. In other words, is the amount by which the extreme value exceeds the threshold u, right? So x minus u is known as the excess, right? So this result due to Pickens 1975 says that conditional probability of x minus u greater than x, given that x is greater than u, right, approaches this as u approaches the upper end point of f, where f is the CDF of x, right? You understand? Yeah. So basically what it says is that given that x is greater than u, which means given that x is an extreme value, the probability that the excess amount is greater than x approaches this point. Okay? I mean, if anything not clear, just let me know, alright? I'm here to help you guys. Okay. Now, if u is large enough, u, remember u denotes the threshold. If you, because u never goes, I mean the upper end point of f can be infinity, but in practice nothing is infinite. I mean nothing in the world is infinity. So you have to take u to be something big enough, right? If u, we can approximate right, we can approximate. So this sign here, it means approximation, because we are taking u, because u cannot be infinity, right? So it has to be something large enough so that you can approximate the left hand side by the right hand side. Okay, so this means right? That's by the definition of conditional probability. Okay, now let me ask you, what is the probability of the event that x is greater than u plus x and x greater than u is what? Is, you should know this from conditional probability, that this is the same as the probability that x is greater than you know that, right? Because the probability x greater than this and the x greater than u is equal to this. Yeah. So this implies that yeah, it implies this. Right, now this is the same as saying okay. And finally, this is the same as saying that fu plus x. Remember here, f denotes capital F denotes the CDF of x. So you can write this as 1 minus this. Okay. So right, and now finally I'm going to make a substitution. I'm going to call this y, right? So I'm going to say y is equal to u plus x. So this will become f at y is approximately equal to Now, if y is equal to u plus x, x will be what? X will be y minus u. Right? And this result here is known as the short GP. Okay, this so this is the generalized parameter model, and this answers the question. You see, I asked a question. The question was, what is the distribution of x when x is greater than u? So the answer to that question is given by the bottom of that page here. So that is here. This is the distribution of x when x is greater than u. Right? You understand? Is that clear? Not clear? Come on, guys. Are you guys clear or not? Some of you still looking at it, scared. Is it? No? Let me know if it's not clear, right? So what I have given in the box, right, is the distribution of the variable x when x is greater than u, right? And that is known as the generalized Pareto model, or the generalized Pareto distribution, right? Okay. Yeah. Okay. All right. So, I mean, I really want to help you guys. So if anything not clear, just feel free to ask me. Okay. And this is. So let me once again write right. So a GP distribution has only two parameters. U is not a parameter. U is just a threshold, right? So the two parameters are sigma, which is a scale parameter, and psi, which is a shape parameter, right? And the notation for that is this, right? This is the notation I shall use to denote a GP, right? Generalized Pareto random variable. Okay. Oh, I forgot my alternate sheet. Just a minute. Give me just a minute, guys. Where's my alternate sheet gone? Alright, guys. So the next thing I'm going to talk about is the domain. It's the same thing as last week when we talked about. Remember when we talked about the GV distribution, we did the same thing. You may recall, yeah. So to find the domain, you need to consider three cases, right? So let's first consider the case where psi is positive, right? So in this case, right, this is the same as saying that this, right, and this is the same as saying that y minus u is greater than minus sigma over psi, and so y is greater than u minus sigma over psi. So the domain is from u minus sigma over psi up to plus infinity, right? You understand, right? That's if you assume that psi is positive, right? This is the domain. Okay. Now, if we assume that if we assume psi is negative, right, then 1 plus right, this becomes and because psi is negative, this becomes y minus u is less than you see why it changes. The sign changes from greater than to less than because psi is a negative number. Okay, right? So this becomes y less than u. Okay, so the domain is from minus infinity to this, right? And finally, if psi is equal to 0, oh, sorry, I made a mistake. You see, I think. Sorry, let me go back to this. Sorry, excuse me. I made a stupid. Well, not stupid, but sorry. Let me go back to this again. All right. The thing is, you should look at this. You should look at this formula here, right? The y. Remember, you should look at the picture here. The picture where I showed you. Where's the picture? Come on. You look at the picture. Y is this is the picture, right? This is definition 2. Yeah, this is definition 2. Now y is an extreme value, so the value for y must be greater than what? Must be greater than u, right? So what I said here, okay, going back to this, right? All right, this is correct, but we must also have a condition. On top of this, we must have a condition that y is also greater than u. So can you please add this also? So this is okay, this is correct, but we must also have a condition that y is greater than u. You understand why? Because y is an extreme value. So to be an extreme value, it must be greater than u, right? So we must have two conditions, right? So y is greater than u, and so in this case, this is correct. Y is, so in the case psi is positive, we have this, and then we also have the condition that y. Sorry. Okay, let me add this. Y greater than u. Y greater than u. Y greater than u. And y greater than u. So what should this be? This is not. So if these two conditions hold, what should this be? It should be. This is not correct. It should be u to infinity. You understand why? Because if y is greater than this and y is greater than this, then the domain must be from u to infinity. Yeah. Okay. Right. Okay. So that's correct. And now, in this case, if psi is less than 0, then we have a problem here. The size, then this should be y Yeah.
I think if y equal to u and x, so x can be less than 0. So y is okay to less than u.
You mean which case? You mean in the first case?
I mean, it says y is equal to u and x, but x is okay that to be less than 0. So y is okay to less than 0.
There's no x here. There's only y. I mean, there's no. I'm only talking about y here. There's no x.
But I mean,
There's no x here. Y is the. What do we define y as? Just I'm a bit confused too. Just a minute.
But psi is less than 0, so it's minus. So we can have a range.
Just a minute. I'm a little bit confused about this.
So the range is u to u minus sigma of psi. It's okay.
Just a minute. I think. If this is positive and psi is negative, you have because this is contradicting, so I think that I'm doing something not right. Oh yeah, okay, I get it. Because psi is negative, right?
Yeah.
So that means this must be u. This must be u. Oh yeah, this must be u. So the domain. Yeah, you're right. Thank you. So the domain for this case is from u to this, right? Because psi is negative. Yeah. And in the case where if psi is 0, then you have this, and the case that y is greater than u. So the domain will be what? This is automatically satisfied, so the domain will be from u to infinity. Is that right? This is correct, madam. Because this is always satisfied. Yeah? Okay? And we have the condition that y is greater than u. So the domain is from u to infinity. Yeah? Yeah, thank you for correcting me. Sometimes, don't know, my head doesn't work. Don't know. So hence, in summary, we can summarize the things like this. So the domain is from u to infinity if psi is greater than or equal to 0, and the domain is from u to u minus sigma over psi if psi is negative. So this is the domain. All right. Sorry for the mistake. I think I did not realize that we should. Yeah. Just, so that's the summary of the domain. Okay. So if psi is greater than or equal to 0, then the domain is from u to infinity. If it's less than 0, then it's from u to u minus sigma psi. Okay? Alright guys. Once again, I'm sorry for the mistakes I made. Okay, the next thing I'm gonna consider is what happens to the, okay, the next thing I'm going to consider is the, should go back to the, you should go back to this, right? I'm going to consider the case that psi equal to 0. I want to know what happens to this formula here when psi becomes 0, right? So f of y becomes 1 minus the probability that x is greater than u times the limit times the limit as psi approaches 0, right? So I'm going to take the limit exact. We came across a similar situation last week. You may remember, right? So this becomes you can write this in this form. Okay, you can write it like this. Okay, the next thing I'm going to do, I'm going to make a substitution. The same substitution I used last week, you may recall. Less m equal to 1 over psi, right? Then this would become alright. If psi goes to 0, then m will go to plus infinity, right? Okay, and then you can write this as 1 minus the probability Right now, from a property I gave you last week, you may recall this. You should have something like this, guys. As m goes to infinity, this goes to the exponential of z, right? So if you use this property, this will become and this will become 1 minus the probability that x is greater than u multiplied by e. Okay, so this is the limiting case of the generalized Pareto distribution when psi is equal to 0, right? Okay, all right, guys. Any questions, let me know, guys, please. Okay. Are you okay, guys? Yeah. Oh, did I pick it up too quickly? Sorry. If it's too quick. I mean, you don't need to copy this down because I always scan it and put it online. So, but if you want to copy it down, that's fine. Yeah. So. Okay, guys. So the next thing I'm going to do is consider is the density function. So far we only talked about the CDF, all right? The next thing to do is to find the density function, or the PDF, the probability density function. So the probability density function is simply the derivative of this, right? So you differentiate the CDF with respect to y. So what do you get? You get I guess, okay. So this is the density of the CD of the generalized Pareto distribution, right? Okay. All right. The next thing is I'm going to consider is the quantile. I told you last week what a quantile is. Do you remember what a quantile is? A quantile is basically you set the CDF equal to P and solve for X, right? Okay, so to find the pth quantile, you set f of y equal to P, and then you solve for y in terms of P, right? Okay, so this will become becomes this, yeah, and this becomes yeah, and this becomes 1 plus okay, and finally this will, if you solve this for y, this will become u plus sigma over psi Alright, so this is the you follow what I've done, right? So I just put the CDF equal to P, and then you solve for y in terms of P, right? And this is the quantile, the pth quantile of the generalized Pareto distribution, right? Okay. So So in particular, the median remember the median of a distribution is corresponds to probability half, right? So you put p equal to half. Okay, so it becomes u alright, so this is the median of the generalized parameter distribution. This is 2, okay, number 2, okay. Alright. The next thing, remember I talked about return level last week. Do you remember the definition of a return level? I told you last week. Hmm? Hmm? Right, this is the definition I gave you. Remember, it's the level t here denotes the number of years, right? T, so t could be 10 years, 100 years, 1,000 years, and so on. So it's the level that is expected to occur once in every t years, right? Okay, now let me ask you, in this case, what is the probability that the variable x, I mean, I should, doesn't matter, right? X is greater than xt. The reason I'm asking you is because this is not the same as the, remember, under definition 1, you should go back to definition 1 of extreme value. There's only one extreme value every year under definition 1. So if you have t years, you have t extreme values. Now under definition 2, you should go back to the picture. Right? This is this is one year. This is one full year, but you don't have, you have multiple extreme values, not just one, right? You have many extreme values in 1 year. So what do you think? So my answer, what do you think this probability will be? Any answer? Come on, guys. It will be 1. this would be 1 divided by m times t, where m is the average number of extremes per year. So in other words, you should go back to this picture, guys. You should go back to this picture. In this picture, m will be, if this is a typical year, right? M will be what? It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. M will be 10. So there are 10 extreme values every year. So out of t years, there will be 10 times t. See, so the probability that x is greater than xt should be 1 over mt. So is all right? Do you guys follow this or not? Yeah. It's the same argument that I used last week, but last week we had only one extreme value every year. So the probability of x greater than xt is just simply 1 over t. Right? It's not the same here. We have multiple extreme values every year, right? So you need to so the probability needs to be 1 divided by mt, right? So that's the same as saying the probability that x is less than xt is 1 minus 1 over mt. So this implies, if you look at this formula here, guys, it will be xt will be equal to, if you use the formula here, right? I'm going to replace p here by this guy here, so it will be u plus sigma over psi okay. So this is the formula. This is the formula for the return level under the generalized Pareto distribution. And you can rewrite it, yeah? Okay. So this is the return level, and the next one is, I will give you a break, but let me do one more. After this, I will give you a break. Okay. All right. The next one is estimation. Okay. Right. Now, there are two, as I said, the generalized Pareto has two parameters, sigma and psi. Right. The likelihood function is so remember, the likelihood is what? It's the product of the density function, right? So you need to have the density function, which is this. This is the product of the density function, and if you take the product, it will be right. This is what you get. The log likelihood function is as follows. So you take the log of the likelihood, so it will be the log of this, so it will be n times the log of the probability that x is greater than u minus n times log of sigma minus okay. Alright, so this is the log likelihood. So the MLEs of sigma and psi are the solutions, or are these simultaneous solutions the partial derivative with respect to sigma equal to 0, and the partial derivative with respect to psi equal to 0, right? So it's the to find the maximum likelihood estimators of the two parameters, you need to solve these two equations, and you should do some mathematics. This is what you will get. Sorry, excuse me. This is what you will get. So this is the partial derivative with respect to sigma, and this is the partial derivative with respect to psi. So call this equation 1 and call this equation 2. Okay. So the MLEs are so the MLEs of sigma and psi are the solutions of 1 and 2, right? And once again, to make things easier for you, there is a package in R which can, there is a command in R language which can do this, find the MLEs for you. So the command is called fpot. Okay. So in I'm sure most of you know R, I guess, right? So there's a command called fpot that you can use so to compute the MLEs of sigma and psi. So you should have a data set. You should have a data set on extreme values under definition 2. So that is like everything that goes above a threshold. Then you can use this command to find the estimates for sigma and psi. You just plug in the data and it will give you the estimates. Right? Okay. Alright guys, any questions so far? So this is this completes definition 2. Next thing I will do after the break is definition 3. Right, definition. So after the break I will do definition 3. Alright guys. Alright. So let's take a 10 minutes break, then after that I will do I've got this is I forgot to give the chocolate for you. You done?
Yeah.
This is okay, thank you. Thank you. That's for the sign. You haven't this is what estimation? No, what is this one? Oh, this is likely, yeah. Sorry, it should be y, yeah. It should be y, yeah. You're right. Do you have any questions? Do you have questions? Yes. Do you have questions? Are you guys okay? Do you have questions? No, this, yeah. The thing is, the probability x greater than u plus x, mu plus x. Sorry. Okay, right here. The probability that x greater than u plus x. Right, this is 1 minus the probability that x less than equal to u plus x. Yeah? And this is the CD. So this is 1 minus f u plus x. That's what I have to do. This is the f is the CD. Remember the f of that, or whatever it is the probability that x is less than equal to 0. So that's what I used here from this line to this line. I used the definition of the CD. I used the definition of the CD. Yeah. F here denotes the CD of x. Capital F is the CD of x. Alright. So this, by definition, is equal to this. Yeah. be big. So I'll talk about this in a minute.
Are you good?
Thank you. Okay, guys. Now we want move on to. So we've done definition 1 and 2. So the next thing is to do definition 3. So I'm gonna start talking about definition 3 now. Okay. All right. So that all of you guys know what the picture is. So this is the picture for definition 3. So the thing here is that this is just an extension of definition 1. Remember, in definition 1, they pick the largest data point, right? But in definition 3, we don't just pick the largest, but we also pick the second largest, third largest, fourth largest, and so on, right? So we pick the first few largest data points, okay? So that's the difference. So suppose you have, let me put it here, and I will explain. So this is definition definition 3, right? So now remember, in definition 1, we use the notation mn to denote the largest extreme value. So because mn, this is the notation. You remember, this is the notation I used to denote the largest data point, right? But here we don't have just largest, but we also have the others. So let me put a superscript. This is the largest data. So this is the largest data in, say, 1 year, okay? And let m right up until so you see what I've done. So I've introduced some notation. So mn1 denotes the largest data, mn2 the second largest, mn3 the third largest, mnr the rth largest. So in that picture over there, r is equal to 5. So because we are picking the first 5 largest data points. Okay. Now the question is, what is the distribution? Because under every definition we are asking the same question, right? We are asking the same question, that what is the distribution of the extreme value? Okay, what's the distribution? In this case, we don't have just one extreme value, we have r extreme value. So we are asking the question, what is the distribution of this? Right, the answer to this question is in the notes. Can I borrow the notes from you guys? I mean, not the note. Yeah, thank you. I'll give it back to you after the class. Don't just remind me in case I forget. In case I forget, I will give it back to you. So the answer to this question is given by the following. It says this is a result due to Weizmann. He is an Israeli mathematician. Says the following: that right. Just give me 1 second. It says that it will take me a while to write it. The probability that should be less than x1, sorry, let me excuse this, in less than x2, right, up to less than xr. Okay, so this is a joint probability because we are looking at the distribution of the joint vector containing the r extreme values. We need to look at the joint probability of this. We need to look at this joint probability, right? And this approaches the following. This is where my eyesight is going to come. It approaches the following. It's a big expression, so please give me some time. As the sum from S1 equal to 0 to 1, the sum from S2 equal to 0 to 2 minus S1 up until the sum from SR minus 1, 0 to R minus 1 minus S1 minus SR minus 2. I mean, this result is on page 9 of the notes I gave you 2 weeks ago. So in case I make a mistake, you can see of the following, which is gamma 2 minus gamma 1 to the power S1 divided by S1 factorial up to the gamma R minus gamma R minus 1 of S R minus 1 divided by S R minus 1 factorial, then exponential of minus gamma R. Alright, so this is the result. So what this say, it says that this joint probability approaches this one as n approaches infinity. Okay, I know it's a pretty nasty expression. I mean, I don't expect you to remember this, so it's just for your curiosity. Alright, so it says that the joint distribution of the R extreme values approaches this, right, where I need to define a few things. So I mean, if you can't read my writing, you can read it from page 9. This bottom of page 9 of the printed notes I gave you a long time ago. Okay. Where 0, 1. So just give me a sec. Excuse me, sorry for taking your time. 1 psi all right. So the gamma I is defined as 1 plus psi. Psi is the shape parameter of xi to the power. This an and bn are the same constants that we saw under the extremal types theorem. Remember when we did extremal types theorem, I defined an an and a bn, and I showed you how to choose them. Like last week, if you were here, I think you guys were here. I showed you formulas on how to choose values for an and bn, right? Okay. So this is the result. So let me call this result star. This is very complicated. I don't expect you to know. I don't expect you to know this result for the exam or for the quizzes. It's really complicated, right? But what it can be shown using star, right? It can be shown that sorry. Right? So based on star, that we can show that the joint density of the R extreme values is given by the following formula, right? Once again, I don't expect you to know how to show this, result, but All right. But the process, I mean, just to explain to you how this formula came about, you may remember last week I showed you how to get the GEV from the ETT. Remember last week we talked about the generalized extreme value distribution and how it combines how it relates to the extremal types theorem. In other words, the three distributions in the extremal types theorem are contained in the generalized extreme value. The same argument here. I mean, this limit, and this is very complicated, obviously. This is very complicated. It can be shown that this result, right, can be rearranged to give you the PDF there, right? In the same way, the argument is the same. That is, in the same way that we got the generalized extreme GEV from the extremal types theorem. This can be used to show that, but again, I don't expect you to know. I don't expect you to know how to show this because it is complicated, right? Okay, but the argument is the same. If you want to know, right? The argument is the same, right? All right. So that's the joint PDF of the, right? The next thing I want to do is, I'm not going too quickly now. The next thing is obviously estimation. So estimation. All right, this is the joint PDF, right? Now to estimate things we need data, right? So suppose this is where the data can come in. Because we are looking at every year, we are picking the first R largest, right? Okay. So suppose so you see what I've done. So this vector here, x11, x12 up to x1r are the R largest data points for the first year, right? And these are this R largest data points for the second year, and so on. This is up to the nth year, right? Suppose there are n years, right? So all these vectors here make up the R largest data points for n years of data, right? So the likelihood what do you think the likelihood will be? The likelihood once again, there are three parameters: mu, sigma, and psi, right? Okay, so the likelihood is gonna be the product for I from one to n, right? Because there are n is the number of years of data that we have, right? Of the following: sigma So I'm copying from this, guys, if you want to see where it comes from. Yeah. Let me change the I to J because I'm already using an I, so I don't want to use the same I here. So I want to change the I here to J, right? So I will say J from 1 to R log sorry, there's no, sorry, I should close here. This is close bracket, right? Then I put a square bracket around here. Okay. So you see what I've done. So this is the same as this one here. So this is the density of the R largest data points in 1 year. But we have n years of data. So we need to take the product of this over the n years, right? So that's what this is. So this is the product of the joint density over there over the n years, right? So that gives you the likelihood, right? Okay. Okay, so you can simplify this if you like. If you simplify this, you get oh, there's a log here and I left out the log. Okay, so this is the simplified form of the likelihood function. Okay, are you with me, guys? Alright, you don't need to copy this down. So I mean, I will scan this and put it online soon after the lecture. Okay, so the log likelihood is just simply the log of this. It would be minus nr times log of sigma. And if you take the log of this, you get minus Yeah, and take the log over here, you get okay. So this is the log likelihood. So the MLEs of mu, sigma, and psi are the simultaneous solutions of the following equations. So you just take the partial derivatives with respect to the three parameters, and so with respect to mu, with respect to sigma, and with respect to psi. Right, so these are the, and once again I have, I'll put it here. Once again I have done the partial derivative, so this is what you would get. So let me call this equation 1, call this equation 2, call this equation 3. Right, so the MLEs okay. So those are the solutions of the three equations. Once again, there are programs in R language which can solve these three equations, but I can't remember the command. I think it's called rlogis or something. But you can find out, right? I'm sure all of you guys are experts. I mean, I can't remember the exact name of the command that actually computes the MLAs in this case, but I'll try to find out next time. I'll try to tell you next time what the commands are, right? Okay, so I'll return this. This is the one to steal this. Yeah, so any questions so far, guys? So this is definition. So this is the end of definition 3. Okay, any questions so far? Yes? No? Just feel free to ask me, guys. Right, okay, next thing I want to talk about, because, alright, the next thing I want to talk about, because we still have about 10 minutes left. So, the thing is that you may remember this. Do you remember this now? Do you remember this, guys? Where does this come from? Huh? These are the conditions I gave you, right? This is the conditions I gave you to check which of the three limits is attained in the extremal types theorem, right? Condition 1, 2, and 3. Okay, and I also gave you some alternative conditions. I gave these conditions also. So these are equivalent conditions, but for checking 1, 2, or 3, right? Okay, now, so what I'm going to say is the following. Now, So we are back to definition 1 now. Actually, we are back to definition 1. I know sometimes I do things in a stupid way because we covered the two all three definitions. Now, in definition 1, there are 3 types of limits, and these are the conditions you need to check. These are the conditions you need to check, right? Sometimes the checking of the 3 conditions can be time consuming, especially in an exam situation. Like if I ask you to find the domain of attraction of something, right? I mean, and you need to check all 3 conditions, right? And it may take a while to check all 3 conditions, right? So the question is, question is to follow. That is there a way to find out that without going through 3 conditions, right? Is there a way to find out that extremal type theorem will hold or not hold, right? I mean, if it's not hold, then all 3 conditions will fail, and right? Okay. Now I'm going to give the answer to this. Okay, the answer is yes. Suppose X is a discrete random variable, right? So okay. Okay. Right. So what it says is the following: that if you have a discrete random variable with upper endpoint w of f, right, then the extremal types theorem will hold if and only if the limit of this as k equals to the upper endpoint is 0. So in other words, if the limit is not 0, then the extremal types theorem will not hold. So it saves you a lot of trouble because in the exam, like if you have to check the 3 conditions, you're gonna spend like 5 minutes on every conditions maybe, so 15 minutes gone, right? Whereas checking this will be easier, right? You have to just check one condition, and if the limit is not equal to 0, then you can say immediately that the extremal types theorem will not hold. So there is no need to check the three conditions, right? You understand? Yeah. Okay. Okay. So let's see. Let me see if I can do an example. Are you ready to go home or not? And let me see if I do an example. Maybe I will do an example now. I will only do the discrete case, but the continuous, there's also a continuous version, but I don't want to do it. I will only do it for discrete distributions, all right? So suppose this is example. And you guys please complete the form. I gave you guys a form to complete. Could you please complete it before you leave? You know this distribution. This is known as the geometric distribution. You've seen this before, right? Yeah. So the question here is, does the ETT hold, right? So in this case, the probability that x equal to k is equal to p times 1 minus p, k minus 1, right? K from 1 to infinity. It can be easily shown. I don't want to spend my time, but you can easily show that W of f is equal to plus infinity in this case. I mean, I'm sure you know how to do it. You know how to find W of f, right? You need to find the CDF and set it equal to 1 and solve. That's how you find it. But okay, so now to check this, we need the limit of k goes to infinity of probability x equal to k is p, yeah, and 1 minus fk minus 1 is this, right? Okay, this is the CDF of the geometric at k minus 1. Okay, you know that, right? So the 1 and the 1 cancel, so this will be the limit as k goes to infinity of which is equal to p, which is not equal to 0. Hence okay, so that's the, I mean, this is a simple example where you have geometric distribution. This is the probability x equal to k, and this is the CDF at k minus 1. So in this case, the limit becomes equal to p, which is not equal to 0, and hence the extremal types theorem does not hold, right? Okay, guys. Tomorrow, did I give you the problem sheet for tomorrow, guys? Did I give you or not? Did I give it to you, all of you? So when you have time, not everything I gave you. Did I? Did I give you? No. So just a minute before you leave. No, it's not here. Did I give you? Okay, I will bring it. I will bring it. Maybe. Just give me a second. Yeah, I don't think I brought it. Here it is here. Just a minute before you leave. It's here. So this is the problem sheet for tomorrow. So if you have time, if you have time, please try to do this before you come to it. I don't think I gave you this one. 1, 2. This is the problem sheet for tomorrow. Okay, please try to work, try to do as many of the problems as you can before you come to the class tomorrow. So we have example card from 5 to 6 tomorrow. Okay. Okay. All right, guys. So have a good day. Before you leave, can you please give me that form, please? That form, then I can. I would appreciate that very much. If you have any questions, just see me. You know how to see me. Okay, thank you very much.